All right, let's get into some GCSE chemistry revision. If you're staring down the barrel of your exams, you are in the right place. Today we're tackling a massive one, Required Practical 6, Paper Chromatography. We're going to break this whole thing down step by step, so you can walk into that exam and absolutely smash it.
So let's start with a really simple question. Imagine you've got a regular black marker pen. Now, you probably know that black ink isn't really black, right? It's actually a mix of a bunch of different colored dyes. But how would you actually prove that? How do you take that single black dot and, unscramble all the colors hidden inside? Well, that's exactly the problem we are going to solve today.
And the answer, the secret weapon we're going to use, is a brilliant technique called chromatography. The name itself is actually a bit of a clue. It literally means color writing. Now, it might sound a bit fancy, but trust me, it's a super powerful and actually pretty simple way to separate out mixtures. It's a huge deal in chemical analysis.
Okay, let's get the official definition out of the way, just so you have it. The textbook says it's a technique used to separate a mixture by passing it through a medium in which the components move at different rates. Phew. But honestly, the best way to think about it is like a chemical race. Seriously. You've got all your different chemicals, the dyes in our ink, lined up at the start. The race begins, and as they travel towards the finish line, they start to spread out. The faster ones pull ahead, the slower ones lag behind. And just like that, our mixture is separated.
Now, for any race, you need two things, right? You need the racetrack itself, and you need the runners. In chromatography, it's exactly the same. The stationary phase is our racetrack. It's the thing that doesn't move. In our practical, that's just the piece of paper. Then you have the mobile phase. This is what actually gets things moving, carrying our runners along. For us, that's going to be the solvent. So what makes one dye faster than another? It all comes down to two things: how well the dye dissolves in the solvent and how much it sticks to the paper. If a dye is really soluble and doesn't stick to the paper much, whoosh, it's going to travel really far, really fast.
Okay, so that's the theory done. Let's get our hands dirty, well, not literally, and talk about the practical itself. This is your step-by-step guide to making sure you get a perfect result, a perfect chromatogram, every single time. All right, let's walk through this together. First up, you grab your piece of chromatography paper, and using a pencil, you draw a line near the bottom, maybe a couple of centimeters up. That's your starting line. Step 2, right in the middle of that pencil line, you put a tiny but really concentrated spot of your ink. Step 3, you carefully lower the paper into a beaker that has a little bit of solvent at the bottom. And this is key. Make sure the solvent level is below your pencil line. And for the final step, you pop a lid or a watch glass on the beaker to stop the solvent from just evaporating away. Then you just sit back and watch the magic happen as the solvent creeps up the paper and separates out that ink. Okay, stop. A super, super important point here. And a classic exam question they love to ask: why did we use a pencil for the starting line? Why not a pen? Well, think about it. If you used an ink pen, what's in that ink? Dyes. So as the solvent moved up, it would dissolve your starting line too, and the whole thing would just become a smeared mess. Your experiment would be ruined. But a pencil, that's made of graphite, and graphite is insoluble. It's not going anywhere, which is exactly what we want. And here's another massive tip for getting those top marks. Remember when I said the solvent level has to be below the pencil line? This is absolutely critical. What do you think would happen if the ink spot itself was sitting in the pool of solvent at the bottom? Well, it wouldn't grease up the paper at all. It would just dissolve and wash away into the beaker. You'd get zero separation and you'd get zero marks. So always check that solvent level.
All right, let's fast forward. You've run the experiment perfectly, you've taken the paper out, you've let it dry. What now? Well, now comes the really important part, the part where we become detectives. We need to analyze the results, to read our chromatogram. This is where the real chemistry kicks in. So what are we actually looking at on this piece of paper? You'll see a few key things we need to name. That pencil line you drew at the start? We now call that the origin line. Then you'll see how high the solvent managed to climb up the paper. That highest point is called the solvent front. It's a really good idea to mark that with your pencil the second you take the paper out, before it dries and disappears. And of course, the most obvious bit, the separated colors, which we just call spots. Each of those spots got to a different height because of that race we talked about earlier.
Okay, so we can see the spots, but to be proper scientists, we need to put some numbers on this. And to do that, we calculate something called the RF value. Now, RF just stands for retention factor, which is a fancy way of saying it's a number that tells us how far a spot moved compared to how far the solvent moved.
The cool thing is, every chemical has its own unique RF value in a particular solvent. It's like a chemical fingerprint that we can use to identify what substances we've got.
And here's the formula. You absolutely have to memorize this one. It's super simple. The RF value equals the distance the substance moved divided by the distance the solvent moved. And remember, both of those distances are always measured from the same place, that origin line at the bottom. Let's try it with some example numbers.
Okay, first things first, let's measure how far our spot traveled. So you get your ruler out, you measure from the origin line right to the center of your colored spot. Let's imagine for this blue spot, we measure 7 centimeters.
Great. Now for the second measurement. We need to know how far the solvent traveled in total. So again, you measure from the origin line, but this time you go all the way up to that solvent front you marked earlier. And let's say that distance is 10 centimeters.
Okay, we have our two numbers. Now we just plug them into that formula we learned. So it's the distance the substance moved, which was 7, divided by the distance the solvent moved, which was 10. Pop that in your calculator, and you get an RF value of 0.7. Simple as that. And a little sanity check for you. Your RF value has to be less than 1. It's impossible for a spot to travel further than the solvent that's carrying it, right? So if you get a number bigger than 1, you've divided the numbers the wrong way around. So, why do we care about all this? What's the point? Well, for your exam, this is massive, because chromatography is a fantastic and really simple way to figure out if a substance is pure or not. And trust me, examiners love asking questions about purity. And honestly, it could not be simpler to tell the difference. Here's the golden rule. If your substance is pure, it will only produce one single spot on the chromatogram. That's it. But if it's an impure substance, a mixture, like our black ink, it's going to separate out into 2 or more spots. So 1 spot equals pure. More than 1 spot equals a mixture. It's that easy.
Okay, let's boil this all down to the absolute must-know takeaways for your exam. Number 1, chromatography is all about separating mixtures. Number 2, pure substances give you 1 spot. Number 3, mixtures give you multiple spots. And number 4, you can identify a substance by calculating its unique RF value. If you can remember those 4 things, you've absolutely nailed this topic. And just before we finish, let's zoom out a bit. This technique isn't just for separating ink in a classroom. It's used all the time in the real world, in forensic science, and making sure our food is safe. So I'll leave you with a final thought to chew on. How could this exact same method be used to test an athlete's urine sample for banned performance-enhancing drugs? It just shows you how powerful this simple little experiment really is.